I apologize for the pause. I'm actually on campus today, and I've got a new computer system in my office, and so I am getting familiar with things. So I do apologize for any pauses, but I am assuming that you can see my screen. I am sharing my screen, correct?
Yes.
Thank you. And so as we learned about the pH scale, it ranges from 0 to 14. And so on the lower end of the pH scale, between 0 and 6, that's where the acidic substances will fall. And the smaller the pH, the more acidic the solution. So a solution with pH 0 is more acidic than a solution with pH 2. And then how much more acidic? Well, because pH is based on the base 10 logarithmic system, a one-digit difference in pH represents a tenfold difference in acidity. And so a solution with a pH 0 is 100 times more acidic than a solution with pH 2. And what that means, as far as mathematically speaking, is that a solution with a pH 0 has a concentration of hydrogen ions, H+, that is 100 times greater than the H+ ion concentration in the solution with pH 2. And so in determining the pH of a solution, one way that you can determine the pH is use a dye, which is usually an organic chemical dye called an indicator. And the indicator dye is going to turn your solution that you're testing the pH for a specific color within a certain pH range. So when you're using an indicator, you can never determine the exact pH of a solution, but you can determine a pH range for a solution. So you can determine, for example, if it's acidic, or if it's about neutral, or if it's basic. So you can determine if a solution of ammonia, you can definitely confirm that it's basic because the indicator will tell you, for example, that its pH is between 8 and 10. And then if you test some orange juice, your indicator will tell you that the orange juice is acidic because its pH will range between 2 and 4. So that's how the indicator will work. It will not tell you the exact pH of a solution, but it'll enable you to estimate the pH range for that solution and therefore be able to determine whether that solution is acidic, basic, or neutral. Another method, of course, is to use a pH paper. pH paper is a little bit more accurate than indicator because with the pH paper, you'll be able to determine the pH however, with no decimal places. So therefore, you'll be able to determine the pH numerically, but not very, very accurately, whereas you get 1 decimal place in addition to the whole number, or 2 decimal places in addition to the whole number. So you'll be able to determine, and sometimes it's not even possible to determine a whole number pH. If the color that the pH paper turns is kind of in between 2 colors, and therefore in between 2 pH numbers, then with pH paper, sometimes you can determine the exact pH, but then with pH paper, sometimes you can only guess or estimate And then the most accurate way to determine the pH, of course, is going to be with the pH meter. The pH meter is not going to tell you the exact whole number value for the pH, but most pH meters can also determine the pH with 1 or even 2 decimal places. Most modern pH meters will give you the reading with 2 decimal places. And so in addition to determining the pH of substances using those 3 methods that we just discussed, you're going to monitor some reactions of acids with some common substances. And so chemical reactions can be both beneficial, especially if they're biochemical reactions that take place inside of the body of a living thing, or of course inside the bodies of humans as well as other organisms. But then chemical reactions can also be detrimental, like the way acid rain, the acid in acid rain reacts with statues and monuments made out of limestone. And so limestone is a base, and then the acid in the acid rain will react with the base and break those statues and monuments down. And so over time, those monuments and statues will have to be refurbished, or basically give them a facelift. The Statue of Liberty is made up of lots of metals in addition to limestone. And acids also react with certain metals. And we're going to observe that as well today, as well as acids reacting with other substances other than metals. And so we're going to be testing marble, which is a building material. It's also used in statues and monuments. And then we're going to be testing a variety of metals and see if they react with our acids. The metals that we're going to test are zinc, copper, iron, and aluminum. And then we're also going to test a protein, egg white. There are various proteins that are a part of what makes up egg white. And so we're going to be observing how the acids react with the proteins in the egg white. And so we're going to monitor these reactions initially, and then we're going to let the reactions sit, and then we'll view them at a later time to see what changes have taken place after those reactions for more than an hour. So that's a summary of the experiments that we'll be observing today. If we were in the lab, of course, eye protection would be very important for this lab because we will be working hands-on with acids and bases, and then using gloves would also be recommended. And anytime you spill an acid or a base, if it's spilled on the desk, then you just want to wipe that spill up immediately with paper towels. And then you would want to rinse those paper towels with water to kind of neutralize the acid or base on the paper towel, and then throw that dirty paper towel in the trash. And then in a lab like this, you want to make sure not only are you wearing your goggles and gloves, but also closed-toe shoes, because you don't want to spill acid or base on your feet. And so those would be the main safety considerations if we were actually in the lab performing this experiment. And so you should have read up on the procedure in this document to be familiar with what you're about to observe in the pictures and videos. And then the last thing you should have done prior to today's lab is completed the pre-lab questions based on the document that we just went over in reading the introductory material as well as reading the procedure. And so, question 1, what would be our answer for question 1?
I have a question.
Yes.
Are we supposed to be seeing like the eLearn site, are we going to be going over like the questions, like what they look like?
Are you seeing the pre-lab assignment documents?
Yes, but they're not opened. Okay.
Are you seeing, am I sharing my screen with you? That's what I'm asking.
Yes.
Okay, so you're seeing pre-lab assignment acids and bases. You're looking at that document, correct?
Not the document, but like what you would be seeing on eLearn.
Okay, so you're seeing my eLearn screen, but not, okay.
Yeah.
So now are you seeing the Adobe PDF file?
Yes, ma'am.
Okay. So what is our answer to question 1? You should already have this done, so I should be getting some feedback.
Hydronium.
Hydronium. And what's the formula for hydronium?
H3O positive.
Very good. H3O with a +1 charge. And so again, the 3 ways that we're going to determine the pH of a solution in today's lab. What were the 3 ways?
Using an indicator.
Indicator is 1.
The paper, the pH paper.
pH paper is the 2nd.
And then the meter.
And the pH meter or pH probe. Either term is correct. That would be the 3rd method, pH meter, or you can say pH probe. Very good. Question 3, based on the pH values listed for these substances, are they acidic, basic, or neutral? What about the rainwater?
Acidic. Right?
Very good. If it's less than 7, then it's acidic. Lemons would also be acidic. What about the pure water at 7?
Neutral.
That would be neutral. The vinegar would also be acidic, but the seawater with a pH of 8.5 greater than 7, the seawater would be basic. And so what is the purpose of an indicator?
To turn a solution a specific color in a specific pH range.
Very good. That is exactly correct. The indicator is going to cause your solution to turn a specific color, and therefore, depending on the color that it changes to, that's going to tell you the pH range for that solution. And she said that exactly correctly. The indicators can only tell you a pH range. It can never tell you the exact pH value. Any questions about number 4? And so one of the acids that we were supposed to use in the last part of our experiment today in testing various acids and how they react, or if they react at all, with common substances, one of the acids that we're supposed to use is nitric acid. However, our technician did not prepare any of that and leave it on the cart for me to use. So we're not going to be observing any nitric acid reactions today. We're just going to be observing hydrochloric acid reacting with common substances, as well as sulfuric acid. However, if we were using nitric acid, and if we were actually in the lab, then we wouldn't want to do those reactions at our desks or at our bench tops. We would want to take the spot plate and add the nitric acid to the common substances underneath a fume hood. And the reason why is because of the toxic gases that could possibly be a product. Nitrous acid and other dangerous acids that may result from the reactions with certain metals. And so that's why we would want to do the reaction under the fume hood, because the fume hood will take those toxic gases out of the room. Whereas if we didn't do the reactions underneath the hood, those toxic gases would stay in the room. And so that's why you would want to do a nitric acid reaction with metals underneath a fume hood for proper ventilation, so that you don't fill the room up with toxic gases. Now, if you ever spill acid on yourself, you need to wash the spill off of yourself immediately with plenty of water. So getting underneath a safety shower would be the correct protocol if you were in the lab and you spilled acid on your clothing. And so getting yourself all wet should be the least of your concern. Your concern should be to wash all of that spilled acid off of yourself, especially if you spill it on exposed skin. Now, spilling it on your clothes, like on your jeans, that material, that fabric will provide a barrier. And so therefore, but also rinsing it off of your jeans is crucial. But if you spill it on your bare skin, then you need to immediately get underneath a safety shower, and you need to stay under that safety shower for several minutes, washing that exposed skin. And you may want to, just to be sure that you don't have a severe burn, is maybe seek some medical attention. But definitely, if you spill acid on yourself, the best way to remedy that is to flush the area with lots of water, and do it immediately to prevent it from absorbing through your skin as much as possible. And so we also learned some common acids and bases in lecture during our study of chapter 5. And so sodium hydroxide, NaOH, would that be an acid? Would it be basic, or would it be a neutral substance? And remember our study.
Basic.
Very good. NaOH is basic. It contains a hydroxide polyatomic ion. And strong bases are known to all have one or more hydroxide ions in its formula. HCl is an acid, is one of 7 strong acids, whereas ammonia, NH3, is a weak base. Sodium chloride would be a neutral ionic compound. And HNO3 is also nitric acid, which is also one of those 7 strong acids. Then we also learned how to name acids. We learned the difference between a binary acid and an oxoacid. A binary acid is an acid like HCl, is composed of only 2 elements. Oxoacids like HNO3 and H2SO4 contain 1 or more oxygen atoms in their formula. So with the binary acids, you name them by first using the prefix hydro to stand for the hydrogen. And so you don't use the full word hydrogen, you use the prefix hydro. And then your second element is chlorine, but then you drop the ine ending of chlorine and you replace it with ic. So hydrochloric. And then you use the word acid. So HCl is hydrochloric acid. And then with the oxoacids, you don't use a prefix hydro at all. With the oxoacids, you base it on the polyatomic ion. That's a part of the formula. So for BNO3 is the nitrate polyatomic ion. So you drop the ending ATE in nitrate and you replace it with ic. So that would be nitric, and then you use the word acid. So nitric acid. And that's the acid that has dangerous toxic fumes, that when you're working with it and reacting it with metals, you want to be doing those reactions underneath the fume hood. Then the final acid, we are going to use that one as well today, along with the HCl, hydrochloric acid, and that is H2SO4. It contains the sulfate polyatomic ion. So again, we drop the 8 ending and replace it with ic. So that's sulfuric acid. And we will be using this acid at 2 different concentrations and see how it reacts with common substances. We're going to use what we call a more dilute concentration, which is the smaller concentration, 0.6 molarity. And then we're going to use it at a higher concentration of 6 molarity and see if there's any difference in the way it reacts with these common substances based on the fact that one version of the acid is more concentrated than the other sample. And so we're going to use 2 different indicators today. What's the name of one of them that we're going to use? Anyone remember? Well, one of them is methyl red. The other is phenolphthalein. Any questions about pre-lab questions 1 through 9? So if there aren't any questions about the pre-lab information, so now you are ready to begin the lab. And so if you go to our Lab eLearn site for week number 12, you have the subcategory for the videos and pictures for the acid-based lab. And so at this time, you can go to your group meeting rooms and you need to watch the videos for determining pH using indicators, using pH paper. Those are 2 videos. And then also view the pictures here for determining pH using a pH probe, which we also call a pH meter. And there are 3 pictures for you to view. And in viewing each of these videos and the pictures, you should be able to determine, using the indicator video, determine the pH range for 3 different substances: tap water, ammonia, and club soda. And then using pH paper, the video shows using pH paper to determine the pH values of the club soda, tap water, and ammonia, plus several other liquids. And then finally, the pH probe or pH meter pictures shows you the exact pH value using a pH meter for tap water, ammonia, and club soda. So work with your group members in watching the videos and viewing the pictures, and with the indicator, determine the pH range of those 3 solutions. And then with the pH paper, determine the exact pH value for several liquids. And then viewing the pictures and recording the pH value for those 3 substances using the pH meter. Once you're done filling out your data sheet, make sure you put your name and your group members' names that you're working with. And then you're to fill out part A, the data table for the indicator tests, which include the color that the indicator turned each of these three solutions, both the methyl red and the phenolphthalein indicator. What color did those solutions turn when I added the indicator? And then based on that color, what's the pH range for those three solutions? Using pH paper, not only are we testing the tap water, ammonia, and club soda, but we're also going to test 6 other liquids: tea, lemon juice, Sprite, vinegar, 0.1 molarity HCl, and 0.1 molarity NaOH. So based on the color that the pH paper turns, determine the pH. And then finally, use the pictures to record the pH values that you see in the pictures for each of those 3 substances. Once you have all of this information filled out for parts A, B, and C on your lab report form, return to the general meeting room, and then we will discuss part D. So I expect you need probably about 20 minutes or so. So let's return to the general meeting room at about 11:50, and then we'll introduce the final part of the lab. Okay, we are back in the general meeting room. So let's discuss your results. So, is there a group that wants to discuss the indicator results that they obtained with us, please? Any group can volunteer. No volunteers to share their results for the indicator portion. We all should have the same answers as far as color of each of the three solutions upon addition of the methyl red and also upon addition of the phenolphthalein. What I'm interested in you sharing mostly is the pH range that you determined. Any volunteers to share? Any questions?
I have one. For the pH, should all of them be just like, for example, like 6.0, like just be a whole number, I guess, instead of like, when we determined the pH using a pH meter, that was 6.59. Like, would any of them be?
Like we discussed in the pre-lab recitation, the pH meter is the only one that's going to give you that kind of accuracy to 2 decimal places.
Okay.
The indicator and the pH paper, the indicator, you're going to have a range. So your answer for a pH range should say for tap water, I'm just throwing out hypothetical value here. I'm not saying that this is the correct answer. I'm just giving you a hypothetical. So for your tap water, you may say that the pH range, based on the color that the tap water turned when you added methyl red, and based on the color that it turned when you add the phenolphthalein, you could say that, okay, the pH range is from 5.1 to 7.2. So with the indicator, you have to give a range, not just a single value. But for the pH paper and meter, you give an exact pH value. And some of these with the pH paper, if you felt that it fell between two colors, like you said, the color is green, but it could be a little bit between 7 and 8, So for the pH paper, you may have some answers that are a range, or you may have some answers that are just one pH value. But with the pH indicator and the pH paper, I don't expect no more than 1 decimal place or just a whole number. But with the meter, you should have written down your answer with 2 decimal places. But again, with the indicator, you must give a range. With the pH paper, your answer may be 1 single pH value. That's just a whole number, or to 1 or just your pH paper will be just a whole number, or it could be a range. If you felt like the color fell between 2 pH values. Does that make sense? So like if you felt that the club soda, for example, was a color that fell between 5 and 6, then you'd say your club soda's pH is 5, between 5 and 6. But if your ammonia was dead on one number, if you felt your ammonia was 10, then you just put the number 10. And so your pH papers, the numbers for pH, I'm not looking for any decimal places for pH paper or for pH range for the indicator. But for that pH meter, you should give the entire reading with 2 decimal places. Okay? Does that answer your question?
Yes, thank you.
Okay. And let's see. Still figuring this out. There's my Adobe. Here we are. So for your indicator part, it was very important that you followed this. This is what you were to use as your guide for methyl red and phenolphthalein to help you decide your pH range. So for the methyl red, your pH value of your substance is between 4.8 and 6. There should be a color change. The methyl red starts out red. And then if you put it in your substance, whether it's the tap water or the ammonia or whatever, if that methyl red turns from red to yellow, then that means your pH range is somewhere between 5 and 6, meaning that it's weakly acidic. To be exact, between 4.8 and 6. However, if your methyl red changes to a more orange color, then you're looking at a color change of between maybe 4 and 6, a pH value between 4 and 6, if you get the orange color. But if your color change is from red to yellow, then you can have a range somewhere between 5 and 7. Orange color will put you right there between that 5 and 6. Now your phenolphthalein, pH 8.2 to 10. If you experience a color change from colorless to pink, or hot pink, or bright pink, or purplish. So therefore, if you get the bright pink or hot pink, then you're going to be somewhere between 10 and 13. If you get a pretty light pink, then you're between 8 and 10. So light pink with phenolphthalein, the pH of your substance is going to be weakly basic, between 8 and 10. If you get a hot pink or a bright pink, then your pH is going to be between 10 and 14. It's going to be strongly basic. Okay. Does that give you a better explanation of the indicators?
Yes, definitely.
Good. So this is what you were supposed to use as your guide in the procedure. That's why it was important to read the procedure before class, because that procedure there and that little portion for the indicators gives you a guide to the indicators. And depending on what color you saw in the video that those substances turned the indicator, that will tell you what your pH range is. So again, for the methyl red, if you saw an orange color change, then your pH is going to be between 5 and about 6. If you saw the yellow color change, then your range is going to be on the higher end, from about 6 to 8. Then the phenolphthalein, if it went from colorless to light pink, then about 8 to 10 pH range. But if you saw a hot pink or a bright pink, pH is about between 10 and 14. You're looking at more of a strong base. Light pink is a weak base. The hot pink, strong base. Okay? Everyone good with the indicator? Any other questions on the indicator portion? Any questions on the pH paper portion? You should have got mainly just a single pH value, just a whole number, no decimal. There may be a few of them that you may have thought may have been more of a range because between two of the colors on the pH paper guide. So which one of those fell into that category for you? Which one of these liquid substances did you feel had more of a pH range rather than a single pH value? Any of them? I would think club soda and tea would be more of a range. Did you observe that same thing? What color did your club soda turn the pH paper? And then what about the tea? Were those both acidic? Now you should be able to answer these questions very quickly because you should have these answers already. Okay. Moving right along then. There shouldn't be any questions about the pH meter. Those answers were very specific. So now that we've done the first parts, A, B, and C, this is a really quick lab today as well. The last part is you're going to be observing reactions of acids with common substances. Now, as I stated, the nitric acid, HNO3, you will not observe any reactions with nitric acid. So for each table where the 6 molar HNO3 is, you can just put a line through that. You're not going to fill out any information on any of these tables for 6 molar nitric acid. So you can just strike a line through 6 molar nitric acid on each of these tables. But you are going to observe 6 molar hydrochloric acid, 6 molar sulfuric acid, and 0.6 molar sulfuric acid reacting with a variety of common substances. The common substances are marble, zinc, copper, iron, and aluminum. And then finally, egg white. Egg whites are mainly protein. So if you're on a low-fat diet and you like to eat eggs, then it's suggested that you only eat the egg white because all the fat in the egg is in the yolk. So if you want to eliminate fat from your diet and you like eggs, eat just the egg white and don't eat the egg yolk. So let's talk about the videos for this part of the lab. And so for the week 12 videos, you go down to this section of videos, reactions of acids with common substances. And the way I've got the videos arranged is by acid. So I've got the reaction of common substances with the 6 molar HCl, and you'll view all of those substances, the marble, the zinc, the copper, the iron, and the aluminum, using 6 molar HCl, then the 6 molar H2SO4, then the 0.6 molar H2SO4. These first videos are all initial observations of these reactions. Then what I did was I let the reaction spot plate just sit for more than an hour. And then I went back and took another video so that you can make your final observations of these reactions. And then I did the egg white separately because when I did the first ones, I didn't have any egg white with me on campus. So I had to go home and get some egg white and come back the next day to do the egg white reaction with those 3 acids. And so this video is the final observations for those other substances. And then this video is the reaction with the egg white, the initial observations. And then I'm about to upload, I almost forgot to do so. I'm going to also upload the video for the final observation of the acids reacting with the egg white. So here's where you'll find all the videos. It's probably helpful to just watch them in the order that they appear. And then fill out your data tables for your initial observations and your final observations. So make sure you fill out each of these data tables for each substance reacting with each of the 3 acids. Here in the first column, your initial observations will be written here. And then the second column, your final observations. And then at the end, once you're done writing your initial and final observations for each of the reactions, then you have your 6 post-lab questions that you need to answer. And so you can now go back to your group lab meeting rooms, watch the videos, making your initial observations of each reaction, as well as your final observations, and then answer questions 1 through 6. And then you can come back to the general meeting room to wrap things up. It's about 12:15 now. I expect you to be done by 1. So I'll be coming into your general meeting, your group meeting rooms, just to see if you have any questions. And once you're done writing your observations, both the initial and the later observations in the data tables, answer those 6 questions with your group members. And then you can return to the general room to ask any questions that you may have as far as your observations are concerned, or questions 1 through 6. This week, you will be uploading your data sheet or your lab report form. And again, as always, please upload 1 single document, a single PDF file, or a single Word document, and then submit it to the Dropbox. There's a link to the Dropbox right underneath the videos and pictures for the acid-base lab under week 12. So there's your link for submitting your lab report. You can also submit the lab report by going to Activities, Dropbox, and there's the acid-base lab Dropbox. If there aren't any questions, you can go ahead and go to your group meeting rooms, watch your videos, complete your data tables, and answer questions 1 through 6. So I see most of you are back in the, excuse me, hold on. Okay, so I've got you back in the general meeting room. Okay. And so you should have your observations, both your initial observations of each substance reacting with 6 molar HCl, 6 molar H2SO4, and 0.6 molar H2SO4. You only had to write a few words for each of your observations. You know, what did you see? Was your solution clear or was it cloudy? Did you see fizzing, bubbling? And then your later time or your final observations. Did the solution look the same? Did it change color? Is it cloudy? Did the metal, you know, did your metal still look the same? Did the marble chips still look the same, or did they get smaller after the plate had sat for several hours? Did your egg white, did it look liquidy at first, and then did it look solid when you made your final observations? Things like that. Just what you saw is good enough. You don't need to write a whole lot, just a few words describing what you saw. Any questions about your observations? And again, you don't have to write anything for the nitric acid because we didn't do that one. So you can just like draw a line through the nitric acid, denoting we didn't do. Or you can just, you know, put a not applicable because we didn't do it. That's fine, okay? But for the other 3 acids for each substance, just give me a few words to describe what you saw. Again, any questions about your observations? And so the last thing that you need to do before you upload your report form as a single document is to answer questions 1 through 6. Any questions about numbers 1 through 6? Did you discuss those with your group members? And so question 1 asks you about the H3O plus concentration range for moderate acids. So as far as acids are concerned, you can describe an acid as being strong or weak or in the middle, moderate. So we know acids, their pH range from 0 to 6, right? So a strong acid is going to have a pH between 0 and 2. A weak acid, 5 and 7. And then moderate would be between 3 and 5. So if your moderate acid pH ranges, we'll say 2 to 5. And then you know that pH is the negative log of the concentration of H plus, and therefore the concentration of H plus is going to be equal to your base 10 function raised to the negative pH power. So on most calculators, just pull up a calculator here. You've got your log function, and unfortunately I can't zoom in with this calculator, but you see the log function log. Right above the log function is a 10 raised to the x power. That's your base 10 function. Most calculators, you've got to hit the shift button to access the base 10. So if my moderate pH values range between 2 and 5, and if I want to know what the H plus concentration is for a pH 2, on my calculator, I go shift and I hit log. That pulls up the base 10, and then negative and pH of 2. So that concentration is going to be 0.01. So therefore, for a pH 2, the concentration of H plus is 0.01. And then for the end of the range, 5, the concentration of H plus is going to be 10 to the negative 5. So again, I go to my calculator. I hit the shift key, then log, and then I put in negative, and then pH 5, I put in 5. And that's going to be 1 times 10 to the negative 5th power, or 0.00001. I'd rather write it in scientific notation. And the concentration units, of course, are molarity. So what is the H3O plus concentration for moderate acids with pH that ranges between 2 and 5? The concentration of H3O plus, which is the same thing as concentration of H plus, is 0.01 to 1 times 10 to the negative 5th. So that's how you were to approach that problem. If you recall in the intro and procedure document, there's your equation that I just used. And again, moles per liter, that's molarity. So again, on your calculator, you just hit your shift and your log key. And that'll pull up that base 10. Then you just hit your negative sign and then put in your pH value. And then your calculator will give you your concentration in units of molarity. Are there any other questions about your post-lab questions 1 through 6? For question 2, they want you to take a look at a comparison between your results and observations that you saw for the 6 molar H2SO4 versus the 0.6 molar H2SO4. This is going to be your concentrated H2SO4, and this is going to be your dilute H2SO4. The concentrated one has the greatest molarity. So did you notice anything different about the reactions of each substance with the more concentrated sulfuric acid versus the dilute? That's what question 2 is asking you. Did you notice the reaction go faster or slower for the more concentrated? So how did the concentration affect the rate or how fast the reaction went? Did you see more bubbling and fizzing for each substance with the 6 molar H2SO4 than you did for the 0.6 molar H2SO4? That's what question 2 is asking you. Question 3, again, based on what you saw, how can the action of acid rain on marble be explained? So your first substance was marble. Acid rain is composed of sulfuric acid, H2SO4. Okay. So what did you see the sulfuric acid do to the marble chip? After you made your later or your final observations, was the marble still present? Could you still see the little white chips, or were they all gone? Had the acid broke those marble chips down? And so statues and monuments, like the Lincoln Memorial, the Washington Memorial in DC, and they're made of marble. Marble has the formula CaCO3. So remember our acid-base reactions that we looked at in the lecture. So the acid what it's going to do, it's going to cause the calcium carbonate to break down. Now, the acid rain also consists of the nitric acid as well, but we didn't observe the nitric acid. So in your answer, just focus on the sulfuric acid. So there's your balanced acid-base reaction. So what that acid is going to do to that marble, it's going to break that marble down into carbon dioxide, and your salt, calcium sulfate. That's your ionic compound, your salt. So remember we said when acids and bases react, your two products are going to be water and a salt. But whenever a carbonate containing compound is your ionic compound, one of your products will also be carbon dioxide. But if your salt does not contain the carbonate ion, CO3 2-, then your products would just be the salt and water. But if your base contains the carbonate ion, then carbon dioxide will also be one of your products. So therefore, acid rain is not only a problem with causing lakes and rivers and even oceans pH to be lowered, which is called ocean acidification. But acid rain also proposes another problem when we talk about our statues and monuments, that they get broken down over time. And acids, as we also saw, react with metals. The Statue of Liberty is made up of lots of metals. And so I know several years ago, I would say a little bit over 20, 25 years ago, I remember this big write-up saying that the Statue of Liberty needed a facelift because the acid rain was peeling off her face over time. And so the Statue of Liberty has had a facelift within the past 20 years. And she'll need another one very soon here. And you notice I've been talking about how acid rain affects monuments. You know, in Washington, D.C., all the monuments are mainly made of marble. And then a lot of other statues, like the Statue of Liberty, made up of a lot of metals as well as marble. And those are all on the East Coast. Acid rain is more of a problem on the East Coast than West Coast and Midwest because the prevailing winds blow from west to east. And so most of the contaminants and precursors to acid rain, like the nitrous, the nitrogen oxides that come from air pollution from automobile exhaust, and the sulfur compounds that come from burning coal that lead to the formation of SO2 and SO3, which react with water to form sulfuric acid, your acid rain, and so on and so forth. The prevailing winds blow those compounds from west coast to east coast, and therefore that's where they mainly get converted into the acids, and therefore fall back to the earth as acid rain. And so because of those prevailing winds blowing from west to east, that's why acid rain is more of a problem on the east coast than on the west coast. And also a lot of the rivers and lakes on the east coast, especially in New England, they contain lots of granite in their riverbeds instead of limestone or marble. And therefore, it's a greater threat to the aquatic life in those bodies of water because you don't have the limestone to neutralize the acid rain. And therefore, the acid rain can really affect the pH of rivers and lakes on the East Coast, more so than the West Coast. So acid rain is an issue, not only for changing the pH values of lakes and rivers, but also in breaking down marble statues. And then talk about question 4, concentration. If you have a high concentration of acid in acid rain, what effect is that going to have on the marble? Will that cause the marble and the statues to break down quicker or slower? And then question 5, metals react with acids, as we saw. Aluminum reacted differently than the other metals. In what way did you see aluminum react differently? Aluminum easily forms a very unreactive oxide coating. How can this account for the observed differences in the reactivity of aluminum? So the coating, the oxide coating, is unreactive. So that means it's like a layer of protection. So when you made your final observations, could you still see the piece of aluminum in the spot plate well, or have the aluminum disappeared? And if you could still see the aluminum, that means that the acid didn't break it down, didn't dissolve it. And that's probably because of this unreactive oxide coating that acts as a layer of protection to protect the aluminum from the acid. Are there any other questions about today's lab? Well, that will bring us then, if there are no other questions, that will bring us to the end of the lab. And so make sure that you have your report form completed, all 6 questions answered, all data tables filled out completely except for the nitric acid components. You can just put an NA in those rows for the nitric acid. And then make sure, of course, that for parts A, B, and C, you have those data tables filled out completely as well. And then make sure you get your report uploaded to the Dropbox with the pre-lab assignment as a part of your report. You're going to turn in the entire document as a single PDF or .doc file, and you have until Friday night, 11:59 p.m. to do so. So if you need to go back and view any of the pictures or watch any of the videos, please do so, and just make sure your report is uploaded by Friday night. And if there are any further questions, you can go back into your group meeting rooms and meet with your group again if you feel you need to, or you are free to leave the meeting. Have a great weekend, and I will see you next week in class or next week in lab.